In the previous chapter, we discussed phenomena where a current produces magnetic field. We discussed few cases where a current produces a magnetic field, and it was a surprise for the scientists who discovered this type of effect. Now, perhaps it was more surprising when the reverse effect was discovered, where a magnetic field can produce an electric field that can drive a current. So this link between a magnetic field and the electric field it produces, or in other words induces, is now called the Faraday's law of induction. So the observations by Michael Faraday and other scientists led this law of basic science, and it has very and in these days most of our applications or we can see most of the applications of our basic sciences. For example, induction is the basis of the electric guitars, and it is also the basis of electric generators, that power cities and transportation lines, and of the huge induction furnaces that are commonly placed in foundries where large amount of metals are melted. So let's examine to understand this concept of induction and to understand Faraday's law of induction. Let's have a look on two experiments which were performed and on the basis of these experiments we can understand Faraday's law of induction. Here in experiment 1 we have conducting loop which is connected to a ammeter. Ammeter is a device which can measure the current. Because there is no battery or other source of EMF included, so there is no current in the circuit. Now, if we move a bar magnet toward the loop, a current is suddenly appears in the circuit, and the current disappears when the magnet stops, when the movement of the magnet stops. So, if we move the magnet away in the opposite direction, a current again suddenly appears in the emitter, but now in the opposite direction. So what we discover? We discover that a current appears only if there is a relative motion between the loop and the magnet. One must move relative to the other, and the current disappears when the relative motion between them ceases. Faster motion produces a greater current. Then if the magnet's north pole toward the loop causes say clockwise current, then moving the north pole away causes counterclockwise current, or moving the south pole toward or away from the loop also causes currents, but in the reverse direction. So the current produced in the loop is called an induced current. The work done per unit charge to produce that current to move the conduction electrons that constitute the current is called an induced EMF, and the process of producing the current and EMF is called induction. Now let's look to the second experiment. Here the apparatus has two conducting loops which are close to each other, and if we turn if we close switch as this one to turn on a current in the right hand loop, this side, the meter suddenly and briefly registers a current, an induced current in the left hand loop here. If we then open the switch, another sudden and brief current, induced current appears in the left hand loop but in the opposite direction. So we get an induced current and an induced EMF only when the current in the right hand loop is changing, either turning on or turning off, and not when it is consistent. It is constant, even if it is very large. So the induced EMF and induced current in these experiments are apparently caused when something change. But what is that something? That one Faraday know, and I think you also know what is the change here. So Faraday realized that an EMF and a current can be induced in a loop, as in these two experiments, by changing the amount of field, magnetic field passing through the loop. So the amount of magnetic field can be visualized in terms of the magnetic field lines passing through the loop. So Faraday's law of induction in terms of these experiments say that an EMF is induced in the loop at the left here here when the number of magnetic field lines that pass through the loop is changing. So what is changing? The number of field lines passing through the loop is changing. The actual number of field lines passing through the loop doesn't matter. The values of the induced EMF and induced current are determined by the rate at which that number changes. So in this experiment, the magnetic field lines spread out from the north pole of the magnet, and as we move the north pole closer to the loop, the number of field lines passing through the loop increases. That increase apparently causes conduction electrons in the loop to move the induced current and provides energy, the induced EMF, for their motion. And when the magnet stops moving, the number of field lines through the loop no longer changes, and the induced current and induced EMF disappear. In the second experiment, when the switch is open, no current, there are no field lines. When we turn on the current in the right hand loop here, the increasing current builds up a magnetic field around that loop and at the left hand loop. While the field builds, the number of magnetic field lines through the left hand loop increases, as in the first experiment. The increase in field lines through that loop apparently induces a current and an EMF there. When the current in the right hand loop here reaches a final steady value, the number of field lines through the left hand loop no longer changes, and the induced current and induced EMF disappear. So this Faraday law can be described in a quantitative way, and for that we need to calculate the amount of magnetic field that passes through a loop. We already discussed such type of situation when we were studying electrostatics, and we know that the amount of electric field that passes through a surface, what does we call that? That is called as the amount of electric field or the number of field lines passes through a surface. So this is called as electric flux, and that was equal to phi E dot dA. Here we define a magnetic flux, and suppose a loop enclosing an area A is placed in a magnetic field, then the magnetic flux through the loop would be E dot dA. Magnetic flux through area A. dA is a vector of magnitude dA, and we know it is perpendicular to differential area. This dA is perpendicular to the surface, as with the like in the case of electric flux, we want the component of the field that passes the surface. So the dot product of the field and the area vector automatically gives us that passing component on the surface. And let's suppose that the loop uh, lies in a plane and that the magnetic field is perpendicular to the plane of the loop. So we can write the dot product here when it is would be dA cos cos theta would be 0 and is equal to b dA when the magnetic field is perpendicular to the plane of the loop, then b and dA becomes parallel to each other. If the magnetic field is uniform, d can be brought out in front of the integral here, and the remaining area just dA, this one just gives the area of the loop. So the phi, this flux would be BA. We already discussed this one previously. And again the unit is 1 Weber. So the with the notion of magnetic flux, we can state Faraday's law in a more quantitative and useful way, and we can say that the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux phi b through the loop changes with time. So the induced EMF tends to oppose the flux change, and Faraday's law is formally written as here. This minus sign indicates the opposition. We neglect the minus sign in this equation. We only seeking the magnitude of the induced EMF. And if we change the magnetic flux through a coil of n turns, an induced EMF appears in every turn, and the total EMF induced in the coil is the sum of these individual induced EMFs. So if the coil is tightly wound, which means it's very closely packed, the same magnetic flux phi b passes through all the turns. So the total EMF induced in the coil would be minus n d phi b over dt. And how there are a few other points how we can change the magnetic flux through a coil. So we can change the magnitude B of the magnetic field within the coil. We can either change the total area of the coil or the portion of that area that lies within the magnetic field, for example by expanding the coil or sliding it into or out of the field. And if we change the angle between the direction of the magnetic field and the plane of the coil by, for example, by rotating the coil so that B is first perpendicular to the plane of the coil and then it is along that plane. So here we can change the magnetic flux through the coil. And if there is a change in magnetic flux or if there is a change in magnetic field lines, then the EMF will be induced. So in our next lecture we will discuss Lenz's law, and we will also do some quantitative analysis of Lenz's law along with a few other topics related to induction.